Chapter number 4, Operational Amplifiers, AC Effects and Limitations. So in chapter number 3, we discussed how the operational amplifier, if we don't assume the ideal conditions, that is, if we don't assume that the gain of the amplifier is open loop gain of the amplifier is infinite, input resistance of the amplifier is infinite, and output resistance is 0. If we don't assume that, if we assume that the actual values of these parameters are used, how those actual values are going to affect the closed loop gains for practical amplifiers, and we discuss the examples of inverting amplifier and non-inverting amplifier. And at the end, as I discussed, we concluded that really at DC or very low frequencies, it does not really matter if you use the actual values or the actual equations, because the exact values using those unideal, non-ideal parameters, and the approximate value using the ideal parameters are just so close to each other that there is no point of going into the extra work that you will have to do to find the exact values of the closed loop gain and all those things. And just using the ideal parameter of an operational amplifier to calculate the closed loop gain, input output resistance, that's perfectly fine. Now in this chapter we will see if your signal is not DC, if your input signal is not DC, rather than it's an AC signal, which actually most of the time is the case, then how, when your operating frequency of the AC signal is increasing, how that is going to affect the closed loop gain and all those parameters of different amplifiers, inverting, non-inverting, and other amplifiers. And that will depend heavily, of course, what are the open loop gain of the operational amplifier as a function of frequency. And as you will see, yes, here it does affect the closed loop gain, because the open loop gain of the operational amplifier does depend on the frequency. The higher the frequency is going to be, the lower the open loop gain becomes. So that's the main discussion in this chapter, and we're also going to discuss the noise in amplifier, internal noise in amplifier, and how does that noise affect the output. And then towards the end we're going to discuss common mode rejection ratio, that is, if both the inputs of the operational amplifier are connected to the same input, we assume that the output should be 0, because operational amplifier is a differential amplifier. But if the output is not 0, so what do we do, and what is the figure of merit, that how good the amplifier is, that is given by the common mode rejection ratio. Again, those are the things that we will discuss in this chapter. So let's start the chapter with the discussion of closed loop frequency response. And in the closed loop frequency response, as we discussed, we will find out the closed loop gain, and here we will assume that the open loop gain, of course, is a function of frequency. So how the open loop gain is described as a function of frequency, it is given by this equation right here. So AJF is the open loop gain at a frequency f, any frequency f. A naught is the gain at DC, which for 741, as we discussed, the typical value is 200,000. And of course, this equation, as we discussed in chapter number 1, this is a low pass one pole circuit equation. F1 is the corner cutoff frequency, or corner frequency, or bandwidth of the circuit. So this is the cutoff frequency. That is, what is cutoff frequency? The frequency at which magnitude of the gain becomes 70.7% of the peak magnitude, which is the magnitude at DC. So cutoff frequency for any filter, low pass filter, high pass filter, cutoff frequency for any filter is basically the frequency at which the gain becomes, or the output voltage becomes, 70.7% of the peak gain if you're calculating gain, and if you're calculating output voltage, then 70.7% of the output voltage, which you can see clearly over here when you take the magnitude of this complex number. What will be the magnitude of this complex number? Magnitude of the numerator, which is a naught, since numerator is not a complex number, and magnitude of the denominator, which will be magnitude of x square 1 plus y square plus f over f1 square, right? So when you take f is equal to f1, this in parentheses is going to become 1, so you're going to have a naught over square root of 2, which is 0.707 or 70.7% of a naught, right? So at f is equal to f1, it will be 1 over square root of 2 of a naught, and f1 is the cutoff frequency. So this is the expression that is used to represent the frequency dependence of the open loop gain of the operational amplifier on the frequency, basically frequency dependence. So it is a low pass filter, single pole low pass filter equation. Okay, now there's a frequency which is called unity gain frequency, and the unity gain frequency is when your open loop gain becomes equal to 1. Open loop gain becomes equal to 1. That's the unity gain frequency, and that unity gain frequency is going to be used very frequently. So remember what is the unity gain frequency. So if you look at, if we plot this equation right here, the magnitude, so basically we are plotting this, we're plotting this thing. So if we plot this magnitude of the open loop gain, then at DC it is a naught, at 0 frequency it is a naught, at f1, which is the cutoff frequency, it is 1 over square root of 2 a naught, and then this is basically the Bode plot right here, and this is the actual plot right here. And then as your frequency is increasing, the open loop gain starts going down, and at some frequency B, which is the unity gain frequency, the magnitude of the gain becomes unity, that is 1. So this is the plot of that equation that I showed you. So right now the discussion of course is the open loop gain, but how we gonna incorporate that open loop gain into the closed loop gain? We're gonna look at that. And before we do that, again this is the same equation. The only thing that we are doing here is we are trying to figure out the relationship between f1, b, and a naught. So in the equation 4.1, which is the equation, the first equation we discussed about the open loop gain, if we evaluate that equation at unity gain frequency b, so we replace f by b. So we're gonna do a naught over 1 plus j b over f1. We take the magnitude of this. This is the magnitude of this, and since b is quite larger than f1, as you can see in there, this is f1, this is b. So in general, b unity gain frequency is quite larger than the cutoff frequency. We can go ahead and ignore this 1, and we can write down that this expression is equivalent to a naught over b over f1. Of course it's a square, so square root and square will cancel each other when you ignore 1. Or in other words, a naught f1 over b is the gain of the amplifier at unity gain frequency. And remember, what is the gain of the amplifier at unity gain frequency? 1. That's why it is unity gain frequency. So this expression is equal to 1, from which we can say that the cutoff frequency is equal to b over a naught. Now b unity gain frequency for 741 is 1 megahertz. So this is 1 megahertz, and typical value of open loop gain, as we discussed, is 200,000. So this is let me go ahead, and this is 1 exponent 6 1 megahertz, and this is 2 exponent 5. So that's going to give you 0.5 exponent 1 or 5 hertz. So observe, only at 5 hertz. So you are at DC, your gain is 200,000 open loop gain. As you start increasing frequency, you get to 5 hertz, such a small difference between DC and 5 hertz. Your gain is already, your open loop gain, that is, your open loop gain has already dropped down to 70.7% of 200,000, 1 over square root of 200,000, right? So at 5 hertz, it is already down to 141,420 from 200,000, right? So you can see that how dependent the open loop gain is on the frequency of your input signal, the operating frequency of the input signal. Okay, so this is the equation from the last chapter, that is the closed loop gain of the circuit. Ideal, non-ideal we discussed, but this is a generic equation. Closed loop gain at DC is equal to the ideal gain at DC closed loop divided by 1 plus Kn over A0. And remember, Kn is the noise gain, and of course A0 is your open loop gain. So this was the generic equation that was developed in the last chapter. Now we know that Kn over A0 is generally quite smaller than 1. We discussed that, right? And we also showed that that's why the ideal gain is approximately equal to the exact value of the gain. ACL DC is the exact value of the gain at the DC. So again, for the sake of simplification, if we assume that ACL DC is equal to ACL ideal, which is very valid approximation, because again they are just so close to each other. Again, why? Because of course Kn is generally quite smaller than open loop gain A0, which is 200,000. So this factor is quite smaller than 1, and when you add 1 into that, it is almost equal to 1. So if we assume that this are equal or almost equal, then we can write the closed loop equation of the gain in terms of the frequency as ACL as a function of frequency f is ACL DC, that is ACL ideal. So ACL DC, we are assuming here ACL ideal value. So let's say for if it's an inverting amplifier, that is going to be negative RF over R1. If it is non-inverting amplifier, it is going to be 1 plus RF over R1. If it is any other amplifier, you calculate the ideal gain of that closed loop gain of that amplifier, and then substitute that over here, and then you can figure out at what frequency what will be the gain at any specific frequency. Alright, so ACL ideal over 1 plus J F over BCL. Again, we are using the same model, that is the one pole low pass model over here. F over BCL. Now BCL is closed loop bandwidth. It is called closed loop bandwidth, not the closed loop gain, but closed loop bandwidth. Why? Again, remember, anything over here in the denominator, 1 plus JF over denominator, that's the cutoff frequency or bandwidth of the circuit filter. Because again, if I replace F by BCL and calculate the magnitude of this, that's going to give me 1 over a square root of 2 of ACL DC. So again, if I'm creating a curve, something like this, so at BCL right here, so this is my at 0, my gain is ACL DC at 0, and then at BCL this gain will be down to 1 over a square root of 2 times ACL DC. So this is my closed loop bandwidth. And what is the closed loop bandwidth? The closed loop bandwidth is defined as the ratio between unity gain bandwidth to the noise gain. Ratio between unity gain bandwidth to the noise gain. And remember, unity gain bandwidth is 1 megahertz. So it's the ratio between, for 741 that is, it's a ratio between, for 741, 1 megahertz over Kn. Whatever the value of Kn is based on the values of different resistors that are connected in the circuit, whichever circuit you are analyzing. So this is our basic equation that we will be used to calculate the closed loop frequency response of circuits at any specific frequency. So let's look at one of the examples. What is the output of the amplifier? Determine the output of the amplifier at 30 kilohertz. And the op amp that we are using is 741. We are not assuming here that A0 is 200,000. We are assuming it is 100,000. Remember, the minimum value we discussed was 50,000, typical value 200,000. It can be anywhere in between. So I just chose a number 100,000 here. And for 741, unity gain frequency B is 1 megahertz. And look at the circuit. So Ri is 100 ohm, Rf is 4 kilo ohm, and the input source is a sinusoidal source, magnitude of 10 millivolt, and frequency of 6000 pi. This 6000 pi, remember, is omega. Omega is 6000 pi, and remember, omega is 2 pi f. That means f is 6000 divided by 2, 3000 pi, or 3 kilohertz. So your frequency here is, operating frequency in hertz is 3 kilohertz. So anytime you are analyzing, and you learn in AC circuits and circuit analysis, anytime you are analyzing a circuit with sinusoidal sources, and you are looking for the steady state response, then you go from the time domain expression to the phasor or polar expression, phasor domain expression. So you take the cosine function that you have, you take the magnitude of that cosine function, and then you take the phase of that cosine function, and that becomes a complex number, polar form of a complex number, and we hide the frequency and we hide the time and all those things. Right now the phase over here is 0, remember. And once we figure out the values in the frequency domain using the complex numbers, then we can go back in the time domain and insert the cosine back, insert the frequency back, and whatever gain that we, or whatever magnitude that we find out, we put that magnitude, and whatever phase we find out, we put that phase with the cosine. So everyone know how to deal with the AC circuits. So in this case, my phasor for input V in j omega is 10 angle 0 millivolt. Okay, so what I'm looking for, first of all, to calculate the gain of the closed loop amplifier ACL DC or ideal divided by 1 plus JF over BC, right? So I'm looking for this F is my 30 kilohertz operating frequency. So I'm looking to calculate the gain at 30 kilohertz, and once I have the gain, then of course I can calculate the output. V out equals ACL JF times V in, right? Because again, gain is the ratio between output and input. So first I'm going to calculate the closed loop bandwidth, or first I'm calculating the ACL DC, the top part, which of course for the inverting amplifier, as you can see, this is inverting amplifier, is RF over RI, negative 40. I'm going to calculate the noise gain, because again BCL is B over noise gain, right? So to calculate BCL, I need noise gain, and again the noise gain for this we calculated we derived in the last chapter and calculated. Remember, if I ask you to show me the derivation of the noise gain calculation, you have to show me, that is, you have to shut down, you have to ground all the input sources, you have to introduce a test source at the non-inverting input, and then calculate the gain V out over test source, and that will be the noise gain. But if I don't ask you, and if you know the expression, then you don't have to show me the derivation, you can just use the expression. So you calculate the noise gain 1 plus RF over Ri as we derived in the last chapter for both inverting and non-inverting amplifier. Remember, it was the same 1 plus RF over Ri, and that is 41. So we calculate the closed loop bandwidth BCL B over Kn, and it came out to be 24.390 kilohertz. So once we have that, we plug in all the values in this equation. ACL DC, which is negative 40, 1 plus J F over BCL. BCL is right here. So this is the equation, and then we evaluated that at 30 kilohertz. So we replaced F by 30 kilohertz, and we solved the complex number, and it came out to be 25.233 angle 129.11 degrees. Now make sure you do that, because it is possible that I made some mistake in the calculation. I'm not double checking anything when I'm working on these, so make sure you do that yourself and then confirm that you're getting the same answer. If not, then please email me and then I'll check my work. Of course, the procedure is still going to be the same, only the numbers are going to be changed if I made any mistake in the calculation. So we go ahead and then we calculate the output voltage, V out j omega ACL j omega times V in j omega, and that is basically this number, ACL j omega times V in j omega. And remember, when you're multiplying two complex numbers which are in the polar form, you multiply the magnitudes and you add the angles. That's how you multiply two polar numbers, two complex numbers that are given in the polar form. So your result is 252.33 angle 129.11 millivolt. Hence the output voltage is going to be in time domain 252.33. That is, you change the magnitude of this, keep the cosine and 6000 pi t same, of course, the frequency is not going to change, and then you add the angle, whatever angle you get. So 129.11 degrees over here, millivolt. So this is how you're going to solve it. Any problem at any frequency that is being asked, that's how you are going to approach that problem.